We're now going into the hottest topic around, which is, of course, AI ML, AML, I call it. And we're very lucky to have the first speaker who is from SDFC. But I just wanted to say that Paul, who I met, fortunately, through this connection, is director of the Ada Lovelace Center. He's worked at Diamond for 18 years, working within the data analysis group, initially before moving to a role on the microfocus beamline, leading the design, build, and commissioning of the NanoPro beamline. And as group leader of the imaging group, working in imaging, he has been involved in several software developments at Diamond and the building of cross-facility activities in imaging, such as tychography, and the focus on software, which has led to his current role. So, Paul, over to you.
Okay, so a bit ahead of time, and I had already cut a lot of slides out, so I'll revert to speaking slowly. So thank you very much for the opportunity to speak today. We have a very exciting program of talks throughout the next few days. Andy gave me this grand title of the state of AI/ML, which I agreed to, and but over lunch, I had a number of questions about what I had included in talk and realized, of course, I'm not really touching on everything that people are doing. This is very much a reflection of just what we're doing, where we think the important areas are. And, this is not trying to get 100 examples in a 40-minute talk. So I guess just to give a little bit of a background to what we're doing, why we're doing it, and to introduce the Ada Lovelace Center. So scientific computing at SDFC is split across two sites. We have the Daresbury site and the Rutherford Appleton lab at Harwell. At Harwell, we have a range of facilities. We've got Diamond Light Source, which has a suite of X-ray beamlines and electron microscopy instruments. We've got the ISIS neutron and muon facility. We have the Central Laser facility, which does high-powered lasers for sort of plasma physics, but also sort of lower-powered lasers for science. So, for example, they can generate EUV and X-ray pulses for things like tychography, so there's a lot of overlaps. They also use EUV for ARPES, so again, there's overlaps for what we're doing on the X-ray facilities. What they've built, or what they're currently building, is a facility called EPAC, which is a petawatt laser with a pulse-driven X-ray source, and that's also going to be used for X-ray tomography. So there's overlaps both in the laser, neutron, and X-ray and electron areas. We additionally have the Rosalind Franklin Institute, which is physical sciences for life sciences. And again, there's a large program in electron microscopy, particularly focusing on tychography. So across the site, there's a number of overlapping activities. And in Daresbury, we have Clara, which is a several hundred MeV electron source, which is for studies related to XFEL design and for therapeutics. And Rudy, which is currently under construction, which is a relativistic MeV electron source, femtosecond electron source for diffraction and imaging. So I think within SDFC scientific computing, there's a long history of community-focused activities. So scientific computing supports activities with CERN, supports activities with the Square Kilometre Array, supports the collaborative computing projects like CCP4 and CCBM. But there was a recognition that our activities were very outward focusing when we had large investments in our facilities and we weren't focusing our computing expertise on those facilities. So to address that, the Ada Lovelace Center was formed with the view of maximizing the output and the impact of those facilities. So how it works in practice is that we have 300 people within the scientific computing division. They're organized into thematic areas. I guess at the top we have, what would be our science or application areas, engineering, biology, maths, AI, materials modeling. And then we have a range of activities, what we would call infrastructure, so software engineering, open science, platforms and services, cybersecurity. And within the program, depending on the needs of the facilities and the activities we want to do, we can pull effort in different ways from these groups to address the challenges of the facilities. So ALC is the facilities-focused activity. PSDI is physical sciences data infrastructure. So that's another large program which is aiming to link together databases around the UK, exactly for activities like AI, and to provide infrastructure for not computing infrastructure, but workflow tools and other activities for UK science. And then there's COSEC, which is the sort of umbrella under which all of the collaborative computing projects sit. So CCP4, CCP-EM, for example, CCP9, which deals with some of the DFT codes. And they similarly have a recent growth in activity to try and push towards exascale codes and to also integrate AI/ML more closely. So we have, a range of overlapping activities towards the facilities, towards the wider community, and towards community codes. Oh, is that okay?
Use that, you don't have to use it.
I'll walk. Yeah, I'll do it. Okay. So what we are, in the sense, is we're a centre of scientific computing expertise. Our goal is to maximise the scientific impact of the STFC large facilities, CLF, Diamond, and ISIS. So I'm mentioning that because when we're trying to design projects, when we're trying to design activities, ultimately we don't have infinite resources, so we're looking for the overlaps where we can find them between the facilities to try and create shared or impactful results. What we're trying to do is, I guess, challenge-driven collaboration. And what I mean there is that when scientists approach scientific computing, they come with what they perceive as their problem, a specific issue. I want you to GPU accelerate this, or I want you to do this specific task, without involving us in the overall bigger challenge. And ultimately, that's where we're sort of, a sense where we're failing. We need to understand the bigger challenge, to understand whether you're actually taking the right approach, to challenge the scientists and what they're doing, but also to take more integrated and interdisciplinary approaches, such as integrating data structures, databases, AI, maths to deliver the solution. And then ultimately, our goal is to develop software for that purpose. So we're trying to facilitate a shift in understanding, advance scientific measurements, advance facility operations and improve the scientific data lifecycle, and importantly, to try and coordinate and collaborate across the site, both within our teams within scientific computing, but really across the site, so that we are tackling the most impactful science and computing challenges. So, like all of the facilities around the world, everywhere is upgrading, everywhere is coming with new challenges. So on the horizon, we have UK XFEL, which is talking about doing megahertz rep rate acquisitions. We have Diamond 2, which is currently an upgrade in progress. The ISIS and Endeavour program, which is bringing a whole suite of new instruments and techniques. The central laser facilities, which are also undergoing significant upgrades for transient studies and X-ray imaging. And all of this is bringing 10 to 100-fold increases in power, flux, brightness. And it's driving people to ask to do faster timescales. It's driving new techniques, new instruments. So I guess the example I like to give when we talk about challenge-led or where AI might make an impact is that in tychography, which is one of the cornerstones for many of the coherent X-ray sources that we're building, if we look at, let's say, CSAC, state-of-the-art at the moment is probably an 80-micron volume, 120 nanometers, at least in a biological material, and it takes you about 24 hours to record that. With upgrades and with new detectors, and in fact, even with new detectors, we've been able to push these acquisition times down to 10 or 15 minutes. But the acquisition of the reconstruction time, so For a tomography, you need to take as usually as many pixels as the image is wide. So let's say we take 2,000 projections. It takes us 5 minutes per projection to reconstruct it, spread it over 8 GPUs. I'm still talking about a day to reconstruct it all, where it takes me 15 minutes to acquire it. So we can't just keep scaling the problem out. We need some different ways of thinking about how we're going to approach this. We also have the problem of if something is 1.5 millimeters in diameter and 10 nanometers in resolution, you've got some, I don't know, 10 to the 5, 10 to the 6 pixels in each direction. You've got a teravoxel image, which is hard to manage. How is the user going to deal with that? How are we going to store it? How are we going to compress it? So there's a whole range of problems, as I say, from the storage through to the visualization, through to the reconstruction, and how we're going to present this to a user. And as was mentioned, I think in the tribute to Bill, was this kind of challenge of the increasing number of non-expert users, right? We have our pioneers, and these are the people that we like to have on the beamlines who come and are willing to do all of the analysis themselves and really work through the problems. And they drive a lot of developments with the facility scientists. And we have the expert users, many of who are applying for grants to develop AI models, which they want to deploy on beamlines. But unfortunately, the majority are still maybe non-experts, and that's being driven by the new science or the new goals that the communities are setting. In battery science, many of the scientists are spending their days in the lab running sort of CV curves, making new materials, and they come to the facility to make a measurement. If that measurement is difficult and they cannot process it, they will just drop it and move on to something else. If you go in and look at nature, look at a study on perovskites, look at a study on battery materials nowadays, you're likely going to see a paper which has electron microscopy, XRF, diffraction, photoluminescence, all in the same paper. Yeah? The sort of days of people being experts in one area are sort of gone, and there's a move towards trying to automate as much as we can. Although I recognize this is slightly, maybe less something that happens in the US and probably more than something that happens in Europe. But there's definitely a push to address this. And ultimately, it's also driven by the fact that the large data volumes we're collecting now are just make it difficult to leave this to the user alone. So I'm just going to fly through some examples, not of AI, but just to say the type of activities the ALC and SCD is doing. So we do energy-resolved neutron CT using iterative regularization approaches. We've developed new approaches for optimizing tychography reconstructions to make sure they're more robust and better outcomes. We have modeling and simulation activities in crystal sort of field excitations, looking at X-ray spectroscopy. We've got the Shape Splice project, which takes small molecules, aggregates them into complex structures, which then can be driven through MD to compare to experimental data. We develop workflow tools in Galaxy, and this one's a prototype of an XAS facility, but also there's the Muon project, which you might have seen earlier today. The data management structures for ISIS and Diamond and CLF, along with data analysis as a service, which is our sort of virtual VM environment that we provide to the facilities. So just covering a range of different activities. So it's an exciting time, lots of new facilities, new approaches, delivering new science, new communities, but ultimately there's this data deluge and analysis challenge. And we're not alone in trying to bridge, merge, and develop these integrated approaches. There's things like Rocket, Big Map, part of the Battery 2030. There's the recently announced Xscope and Illum, I think it is, from Slack. And there's other activities like Diamond, Diadem in France, in the CNRS. So lots of people are recognizing the need to sort of push AI, push integrated approaches to deal with problems. So Our particular strengths are clearly we have imaging across the sites. This is something we're trying to push. We're quite strong in computational biology, and we have this unique sort of co-location of facilities in terms of lasers, X-rays, electrons, and neutrons. Our particular strengths are in theory and simulation, maths and AI, and sort of these platforms and services. So in terms of developing AI, I guess the Ada Lovelace Centre is going through a transition at the moment. So we started in the past just doing projects from, we would get contacted by scientists, we do a project, and we would kick off the project, and then ultimately to be a question about whether something comes out. So when we've tried to engage again with facilities, there's been a sort of a bit more of a pushback this time and problematics around how we're actually going to deliver this. So ultimately, there's a recognition from many of the scientists now that they don't really have enough data, or there isn't enough metadata to do something sensible, or where people think they have data, the volumes are just too small for us to do anything. There's the accuracy explainability problem. In areas like imaging, there's a concern that you're not generating artifact-free results, and ultimately there's a reluctance and a skepticism to adopt machine learning approaches. In terms of automation, there's concerns around what this will do for the communities longer term. Certainly this is maybe something that's happened in MX, but do we want to do this more broadly? And ultimately, many of the AI methods, they have a hit rate, a success rate, and the question is, well, if I just train the user and they get, do I get 100% hit rate, and why am I doing this? We also have some challenges with the AI hammer. I mean, that most of the problems, or many of the problems we deal with, could be solved with conventional maths, but people seem to just jump straight to AI, and we need to triage these a little bit better. For the UK, there's this question of carbon footprint and how we're going to pay for AI in the longer term. And the reproducibility problem comes up time and time again, where people try and replicate or take a model that they've read in the paper. It becomes difficult to use, it didn't quite work as they wanted, or in the other case is I've read a paper and I want to do this, and it's very hard for us to assess whether it's actually worth doing. So, I mean, where we sort of are in this loop is much of what we're doing is this in this triaging prototyping phase. Much of the time we're spending a large chunk of the project just trying to get the data and prepare the data, trying to train and validate. But whether many of these models actually make it into production is a question. And there's the issues we have around the infrastructure needed to push to production, the culture and the need to monitor and to identify gaps, and then to feed back and improve the AI. So structurally, what we're sort of looking at from the conversations, and I think these are very similar across many of the facilities, in terms of where we think we can make transformative change, and the first one is probably expanding the reach of simulation. So simulation tools are traditionally computationally intensive, often need an expert. And this is an area where we think we can accelerate adoption of simulation and can use it to enhance the interpretation and design of experiments. Foundation models, I mean, LLMs, we're going to have a talk about after this, about this, and ultimately there's a lot we believe we can do around text to action and guidance, and that to transform the support and both in the experiments and the analysis. Reducing barriers tends to be focused on high data rate experiments, so driving edge computing, inference-driven analysis to try and reduce the computational load. Optimal use of resources, digital twins and surrogates and some of the activities, and reinforcement learning, smart experiments to try and to choose the optimal outcome and goals. And as I said, probably the other big challenge for us is the ecosystem. The ML ops, making sure that we've got this not just prototyping, but validation, sharing, reuse, continuous learning, along with the associated curation tools, and really embedding AI in every sort of data generation process. So I would, I mean, ultimately, if LLM tools are going to work, and I suppose my dream would be that I was a beamline scientist for many years, and my role was reading nonsensical grey log entries to work out why something had failed, and working out that means to turn something on or off. It would be really nice if, you know, people thought about the log entries that they made, and we could maybe try and build some sense about how we deal with software. Telling people an experiment had saturated the detector. Just writing code and writing scripts for users. So ultimately, you know, if we do this right, and the role of the instrument scientist at a facility will change significantly, because many of these tasks can go, but it needs embedding of that thought process of how the AI is going to help in all of our activities. Okay, so I'm going to talk a little bit about expanding the impact to simulations and experiments. So across the facilities, and this is just a subset of some of the tools we provide, we use density functional theory, we use molecular dynamics to support experiments. So people do DFT calculations, which then supports the sort of inelastic neutron scattering calculations. We do MD for disordered materials, which can be used in sort of XPDF and the sort of similar studies that within neutrons. We do DFT for muon galaxy. We can, you know, there are opportunities, for example, to do DFT to estimate when a state change might happen in a high pressure cell. So you can select where the temperature or pressure range is to help you reduce the amount of time you're sort of ramping up an experiment. And areas like XANES, RPAs, and so on, many of those, well, at least XANES, traditionally has been very much a hand-waving fingerprinting technique where people point the bumps and say what they mean, but they don't necessarily use simulation modeling to understand the data. So I'm pointing to this because one of the primary issues I guess we had was that the availability of data has meant that most of our AI activities have been areas where we can simulate rather than areas where we can use data. And so simulation is sort of a rich area for us to make progress and drive things forward. So the starting point for much of what we want to do has been the materials project. So the material project captures a few, I think, 150,000 or whatever it is, number of DFT calculations. Captures calculations, XANES and XAFs. It captures a range of material modeling information. And from this database, you've got a simple API. You can pull the information out and use that to move things forward. So the area that is moving forward for us, and an area that we will use to try and impact the facilities, is machine-learned interatomic potentials. So traditional MD, the accuracy is usually it's semi-empirical. You sometimes have to tune it. The accuracy is moderate. DFT is a little bit more of a gold standard. But with machine-learned interatomic potentials, you can build molecular dynamics which has the accuracy of DFT. And so it allows you to do activities which were traditionally taking sort of days or weeks in minutes. So geometry optimization, MD for vibrational studies, and other areas. And so many of the codes that we already have, which use MD in some way, can integrate machine-learned potentials to expand the timescales, expand the spatial ranges, or expand the activities. So the types of examples is looking at phonon calculations, CO2 capture in MOFs, something that would take weeks, takes a few minutes. Other studies, deprotonation, thermal conductivity, and so on, are all made possible by these machine-learned potentials. So as a snapshot, one of the things they do very well as a community is that they have very well-defined benchmarks, and those benchmarks have created a leaderboard. So if you're developing machine learning potential, you have sets of curated data. You can run the benchmark and rank your model on the benchmark. So you have a pretty universal way of knowing if your model is the best and where it sits in the scale. And this is driving competitive development. So the paper that came out describing MapBench in 2023 has a completely different list than you'll find now, because people are continuously driving and pushing forward this machine learning potential development. And the leaderboard ultimately is changing every sort of 3 to 6 months. I guess a thing to point out is that when we include the commercial vendors in the leaderboard, they dominate the top 3 positions. So Orbital Materials, MatterSim, which is Microsoft, GNOME, which is Google, are making considerable efforts and accelerating in a number of areas, not just large language models, but also materials discovery. Which does raise a question, I guess, about the resourcing and whether they're just going to move at a much higher pace than we can. So I just wanted to give a little bit about materials discovery. I felt maybe I probably won't overlap too much with some of the things that are being discussed, but just to give a snapshot of where some things are. Because we talk about materials discovery all the time in terms of what we're going to do at facilities. So towards the end of last year, Google published this work, Scaling Deep Learning for Materials Discovery, where they effectively used graph neural networks, generated structures, determined their stability, and ultimately built a range of sort of stable structures and potentials. Now, I mean, there is an open question about this. I guess one thing is whether these is really materials discovery is a question. And what I mean by that is, while we discover new compounds, we still don't have the pictures of, let's say, what those materials actually behave like. So this doesn't tell us whether this material has a particular optical property, doesn't tell us how it will crack, doesn't tell us its microstructure when we propose it. So I guess we're still quite a bit of a way from real materials discovery, and there's a big role for facilities that have in that in terms of tomography, RPEs, and all the other measurements we take of properties. The follow-up paper from this was this autonomous materials discovery with the A Lab, which is a really sort of, a pioneering experiment where they took these models, they took text mining, and effectively they tried to automate the synthesis of new materials. So they would look at reaction pathways, they would tune temperatures and so on, then they would measure the powder X-ray diffraction data and so on, and iterate to try and make new structures, new phases. Now, this is a really pioneering experiment, came out towards the end of last year. They published all of the data, and one of the challenges was that in the end, it turned out that most of the phases that they predicted were wrong. Right? And they were wrong because if you look at the powder X-ray diffraction, you'll see there's quite significant errors in it. And they were wrong because they based all of their models on Materials Project. Materials Project is based on DFT, which only allows you to have ordered structures, small structures. And that fed into the model and didn't account for fractional ordering or other effects which occur in powder diffraction. So, I mean, I guess the message is still that there's still a long way to go towards automation, and you really need to get those basics right. And, last week, there's a paper published which outlines a method called crystallize, where, again, they've tried to automate the process of determining powder X-ray diffraction patterns. And this still does not deal with preferred orientations. It doesn't deal with fractional occupation. It only deals with ordered materials. And it has, I think, a 67% success rate. And it doesn't deal with multi-phase materials. So you have to remove your known phases from the powder diffraction before you analyze it. So again, I think I just wanted to give this as a snapshot of where we are, right? It's often, powder diffraction is often picked up as one of those areas where we should be able to accelerate and move quickly. But the models and systems are still, have a bit to go in terms of building those base structures. Another example, I guess, I thought was useful just to talk about was in terms of how sometimes how uncertain the way forward is laser-driven systems. So you can excite a system with a pulse, you get a sort of dipole moment over time, and the question is, could machine learning help with this? Because this is quite a long calculation for us to do using time-dependent density functional theory. So the equations I won't bother you with, but ultimately you've got a partial differential equation, and the question was, can you actually solve this more quickly with machine learning? So we sat in a room with our mathematical team and our machine learning team, and our mathematics team pointed us to this paper, which came out earlier this year, which basically says that no, you can't beat PDEs with machine learning. Ultimately, finite element methods are better. But the machine learning people had read papers which said something differently. So they went ahead and played around with the problem. And I will say it did take them a while to flick through. But what we were able to do was get a preliminary result which shows that, yes, in principle, we can predict or infer the dipole as a function of time successfully with machine learning. And that takes those calculations, which previously would take days, down to a few minutes. So that's, again, opening up opportunities for us in terms of how we interpret experiments. And the last kind of push we're making in simulation is Goldilocks. Hopefully most of you know the porridge story. But what we're aiming to do is build input files for DFT automatically. So this is in part due to the fact that a large portion of the code we run is DFT. There's a kind of an energy consumption question around under and over convergence. And if we can design models that pick optimal sampling and large models that build configuration files, we can make this whole process much easier for people to use. Okay, so in terms of segmentation, I think we've all in various facilities been involved in projects looking at fusion, looking at segmenting X-ray or neutron images. And the question that keeps coming up is, can machine learning-based auto-segmentations work? I mean, if they're trained on real pictures, do they really work on neutron and X-ray data? And I think our machine learning people will say, no, there's just too much systematic noise, and there's just ultra-low sort of semantic context. It's just not designed to look at the tracks. So, I mean, we've been doing some developments in this space. I guess it doesn't really matter. But I guess, again, looking back at foundation models, Meta released the segment anything model back in 2023. And again, I guess there's a question that with generalization, that they don't tend to work that well on microscopy and X-ray images. So in the medical space, there's examples where they've had to, it provides a good platform where you retrain it. But in the microscopy space and the medical space, they generally need to be retrained for the specific problem. So the challenge, I think, for us is that we have limited availability of labeled training data sets in order to push this forward. Okay, so there are, oh, sorry, I got this one, sorry. So we're going to hear a little bit later about sort of autonomous, various autonomous projects and controls. And this was a project we did with the FTIR beamline. It has 2 deformable mirrors, each are 97 sort of actuators, and the challenge was being able to align and focus those mirrors. So effectively we had to build a surrogate of how the model deformed the image. We wanted to sort of aim for a sort of flat top hat beam image, and used sort of Bayesian optimization to tune the mirror. So effectively, we would actuate the 97 actuators in lots of positions, record all the images, build a digital model, and then use the Bayesian optimization to tune the mirror. So we got much better results than traditional methods like Adam. Yeah, I think we can read this. So just to show what this looks like in practice. So to try and achieve a uniform intensity in real time, it just drives the mirror, redistributes the intensity. It's inside the window. And this is, I'm glad to say, this is a deployed solution. This is something that's used on the IR beamline. There are 2 mirrors, each does it. The first version of this had no physics in it, so it's effectively just learning how to refocus a mirror, but it's not necessarily accounting for any coherence or wavefront effects, which needs to be it needs to do next. Okay. Okay. So I guess I'm coming to the end. So infrastructure, I think. Many of the things we're doing, you've already heard about workflows. What we're trying to do is link together not just our FAIR data, but the provenance. So Galaxy project, i.e. the workflow hubs and the workflow crates, Argo and MFlow to build provenance and organized structures. We have projects looking at federated learning in a couple of areas now. Ultimately, this is an effort to try and reduce the energy by locally training, uploading those resulting weights and aggregating the model, and ultimately looking to build sort of community-focused projects where we're sort of minimizing the data sharing. And the other area we're trying to grow in the ML team is physics-informed ML. And again, this is to attack the problems of limited data, the generalizability, and so on. Okay. So I think simulation is currently driving most of our activities. We don't yet have sufficient data to do enough, many of the activities we want to do. Open approaches are driving AI development, in particular materials projects and the related activities. Open benchmarking and validation is helping to drive trust and adoption, and that's hopefully going to, and in general, that's an area we need to address some of the skepticism. We need to strongly couple AI, maths, and domain expertise because we keep coming across instances where the root problems aren't as well understood as they could be. In terms of the foundation models that have been out there, like Segment Anything, they're not quite the sort of panacea we were hoping for, but they are good base structures in which we can fine-tune towards the problems we want to solve. And ultimately, understanding your core assumptions and gaps in your training data is important. And I think where we are in terms of, if we look at the power of diffraction, if we look at tychography and the related problems, the human in the loop is still there. There isn't yet full automation, and maybe the model we should be looking at for going forward is guided analysis and guided training. Okay, with that, I'll just say thank you. There's collaboration opportunities with ALC. I think we're walking across facilities and looking for common solutions. There's more work to do, but I think things are going in the right direction. And just to say thanks to SciML, the materials modeling team, and the ALC team. Thank you.
Okay, we're good in time, so we can take some questions. Yeah.
Thanks for your talk. Very nice. I would like to ask a question about why don't we use, instead of DFT, going to second principles simulations or semi-empirical methods that are way cheaper than the former?
I mean, I think it depends on the problem and the accuracy that you need for the parameter you're trying to determine. Yeah, I mean, by and large, I mean, the DFT is often a starting point for what we're doing. We're using the outputs to then calculate other values, other parameters. So, yeah, I think it depends on the problem and the parameter.
Yeah. Stefan.
Thanks for the nice overview presentation. You hinted a bit at it. Our facilities produce a lot of data, most of which will be open access at some point in time. And you have companies like Google, Microsoft using this to train their models and exceeding open source models. I don't expect a general answer, but what's your feeling? Is this something we need to start considering more, something we just can't avoid, something which is even beneficial maybe?
Yeah, I think we can't avoid it, and in some places it will be beneficial. Again, it's not clear yet. Like I said, with things like the segment anything model, which Facebook or Meta created, I think they did 11 million images, 1 billion segmentations. So that's a pretty large model, and it still doesn't cover a lot of what we want to do. And so it's not, it's not clear whether Meta are going to retrain on medical images or X-ray tomography images. And, as I say, we don't have that data anyway at the moment. I mean, I would say, like, what we should be doing is reusing them where we can. I mean, I think the segment anything model is a good at recognizing shapes. It can be used as a starting point for segmentation, and ultimately, yeah, I think that's probably where we're going to be. That in many cases they're a starting point or a useful tool.
Other questions? Yeah, Saulus.
Okay. Thanks for the talk, very interesting. And just a wild thought, you mentioned that AI needs to be coupled stronger with classical math models, which sounds very reasonable. And I understand that currently we have two options. So either we have a classical algorithm based on known mathematics and physics, and we segment image based on that, or we train with a lot of data the AI to give us the final answer, the final segmentation, for example. Is there a possibility that we train AI to derive a math-based model, which will then do the understandable and predictable segmentation?
Well, I mean, I guess that's the dream, isn't it? Yeah, I mean, they're certainly getting better and better, and I think that's probably, there's definitely views that we're going to have, where we have lots of models in the future, we may have a few super trained models which can answer all these complex maths questions. So perhaps that's something that's coming in the future, but yes, for now, I'm not sure.
I had a question, which was, the Gartner plot of hype when you have a new technology and you go down and you come up into a steady state. Do you think the hype in AI, we getting close to the maximum, or are we still going to go higher?
It depends. I'd probably say if you're management, you're probably lower down and want to push for. If you're people who are on the front line, you're probably a bit higher up. Yeah. There's probably a bit of both, yeah.
So deception is coming, yeah.
Yeah. Well, as I say, when we went out to the facilities and in many cases talked about AI, and particularly when we engage with a lot of the imaging groups, I'd expected a much stronger reaction to people saying, can we apply AI here now? But as I said, many of it's been sort of skepticism now about whether it's actually going to work. And I think that's a little bit down to sort of using, perhaps using previously models that maybe weren't trained in as much data, didn't give good results, or seeing artifacts and then questioning whether this is ever going to work. And so, so I think we're getting, there's a little bit of skepticism at the moment.
Okay, I think in the interest of time, we can thank Paul again for an excellent talk.